In the late 80s, Electric Power Research Institute asked Hendrix to move from 46, we were only at 46, up to 69 kV. So we had a joint R&D project with Florida Power and Light. We used their labs down in Juneau. And 69 kV spacer cable, we now have 69 kV all over the place. In 2007, Hendrix was asked by BPA to develop 115 kV high voltage current conductor. So we submitted a joint funding statement to the Department of Energy jointly with the BPA, but we were turned down and we decided to go it alone. From 17 to 2024, system design was complete, patents acquired, pilot was installed at Versant, formerly Emera in Maine, in 2019 with PD monitoring every 3 months. We just recently finished Liberty Utilities there, rail trail 2.5 mile 115 kV spacer cable circuit. What are our objectives? Why do we want transmission spacer cable? What are the motivating factors? Well, first of all, we want to minimize our right-of-way requirements. We want to have the ability to add circuits in an existing right-of-way. Maybe put a new pole line or multiple circuits on an existing pole line. Maybe we're going to use a voltage upgrade in that same right-of-way. We got a 15, 25, 35 kV right-of-way. Maybe convert that to 69 with a 15 kV below. And the ability to add a circuit without increasing pole height. Number 3, we want to have reactive voltage support and improve voltage regulation. We know that when we bring the phase conductors closer together, we're canceling out the 15 to 20% of the impedance, and therefore the voltage at the end of the line is 15 to 20% higher. We've got a better power factor. The cap banks are switching on and off less frequently. The tap changers at the sub are banging around a lot less. So it's got all kinds of benefits there. We have improved reliability, ability to withstand momentary contact with trees and animals without faulting. We want to reduce tree trimming. We want to increase the tree trim cycle length. There's a benefit that's not talked about anymore. It was a big deal 20 years ago. Reduction of magnetic fields, 80% reduction compared to bare wire, 95% reduction compared to underground. Number 7, we're talking about environmental stewardship. We want to protect the flora and the fauna. How about reducing the carbon footprint? Closed phase spacing can significantly reduce pole heights. There's dollar savings, lower profile, improved aesthetics. And lastly, we're using covered conductor and transmission, essentially where underground or bare overhead is either too costly or implementation is near impossible. As we go from 15, 25, 35, 46 up to 69, let's talk about it. 69 kV is the same exact system that we're using at 15 kV. Spaces are a little bit bigger. Insulation's a little thicker, but it's the same compact system. We have the same exact covered phase conductors. The same exact messenger, might be a little bigger. The same spacers, they're designed a little bit differently. It's mechanically strong, and it gives us high reliability. That's what it looks like. Our design spec, the cable, 960 kV BIL, a 218 kV AC breakdown. The messenger, the same messenger that we're using at lower voltages. It's AWA, aluminum-weld aluminum. It's the mechanical strength messenger member of the system that holds everything up. Because we're using aluminum-weld aluminum, it's a high ampacity. It has a low surge impedance. We started using it in coastal areas, industrial areas. It has a very high corrosion resistance. You're not going to rot out a steel core. It's coated. And again, it's a system neutral ground lightning shield, and it provides protection for the phase conductors above. Now, the one-piece spacer that you saw at the distribution voltages is gone now. So our first spacer was back when we were still using ring ties back in the last century. It's made of high-density polyethylene, the same dielectric constant as the conductor. It's got a long leakage distance, and we use the same self-washing shed design. In 2009, we said, hey, it's time to get rid of that ring tie and make it ring tie-less like our other voltages. So we wanted to increase the leakage distance because we wanted to get into areas that were bit more contaminated. We wanted to put more fins on the horizontal beams, and we wanted to put that good old DM clamp on the messenger. You see the circle around here, and that's going to get us, when you hook that on the messenger, it can't roll backwards or forwards. So now we have more positive staying power of that spacer where it belongs rather than having the ability to move. So that was the That was the second version. The third version just came up 2 years ago. We said, hey, we want to prevent twisting of the spacer close to the poles. We also want to be able to support larger conductor sizes. We're going to be building transmission lines, not with 795 and 954, but at some point, 1192, 1350, 1510. So we want to support larger conductor sizes that are, anticipated for bulk transmission loads. So what we did is we put two arms in the center, were replaced by a single arm with reinforced fiberglass. And that reinforced fiberglass can really, really hold an unbelievable amount of load and compression. We ran the mechanical FEA and tensile tests on the new design. We will do electrical tests at some point, which will apparently be a waste of money, since when you do the BIL and 60 Hertz withstand tests on a spacer, the only thing you're testing is the air. And we have those from the same dimensions, but in any case, and those are the areas of improvement. So you can see that center beam is really massively reinforced. And I'm not going to show you the FEA, the finite element runs, but we increased that by a good 5x, the mechanical strength. So it's wonderful.